Good day to you all. Today I'm going to be going over some of the basics of conservation of mass, and I am assuming you have some familiarity with calculus. Mass is a property of a system, roughly equivalent to how much stuff is present. It is an extensive property, meaning it's additive across the entire system. More stuff in the system will generally mean more mass, and we represent that with the volumetric integral of the density function. We can assume a constant density function for most purposes, giving us rho v for our mass. In a closed system, mass cannot be created, nor can it be destroyed. It must be conserved. However, if we allow the system to be open, mass can be transported both into and out of the system across system borders. This means msys is not necessarily constant, and so will have a non-zero time derivative. We can solve this using our equality from earlier, taking the derivative of rho v, and then applying the product rule, we find that rho dv dt plus v d rho dt is equivalent to the change of our mass. We can reassert our constant density function assumption and remove the second term of that. Since we're in the time derivative, we'll also need to find the derivatives of our mass transport terms, and we commonly denote these with dot notation, where a dot refers to a time derivative. So we can find conservation of mass in rate form, and when the mass in and mass out are equivalent, there is no change in msys. The system will be steady state. As an example, let's look at the case of water being poured into a glass. At what rate is the surface of the water rising? We have mass flowing into the system, so we know it's an open system, and there's accumulation within the system, so it's not steady state. We have two options for our system boundary here. We're going to start with just taking the interior of the glass as our system. We can represent the mass inside our system as the sum of two sections of mass, because mass is an extensive property. We can take the derivative of our two mass functions, assuming our constant density. We can assume a constant cross-sectional area to turn it into an area times a height. To use this height, we need to assume a datum, and here I've shown datums for h1 and h2. We know that h dot, the time derivative of h, will be equivalent to itself because that bar will be moving. It'll just be a negative sign. So we can make that substitution, and then we find the right side of the equation just by taking all of our terms in, all the terms crossing system boundaries, and we find that dm sys dt is m dot in. So we put the two sides of the equation together, just substituting for dm sys dt, and we find that rho a1 h dot minus rho a2 h dot is m dot in. So we can solve these for h dot, and we've solved our problem. For our second option, we can consider only the water that's accumulated inside the glass as our system. To account for the fact that the surface is rising, and we don't want to measure just the bottom of the water in the glass, we define the top surface of our boundary as mobile. I'll skip a few of the substitution steps shown earlier. The mass inside our system is just the entire sitting body of water, rho times the area times the height. We can take the time derivative of this, and when we do the right side, we have to be careful. When we move the boundary up, yes, that's because of m dot in, but we also have to account for the fact that there's already a column of water that we're moving into. So we need to move that into our input term, our crossing system borders term. We substitute these equations into each other, just replacing dm sys dt, and we solve it again for h dot. Our answers here are identical, which is a very, very good sign. That's it for the very basics of conservation of mass. Thank you for being here. I hope you found what you wanted, be it entertainment or information. A link to the next part, if it's available, is on your screen right now. All of my content is free to access and without advertising, and the plan is to keep it that way. However, if you're feeling generous and want to help support my content, feel free to send some spare change my way through the links in the description.